Well, in the previous PPT, we were studying about the two types of fermenters, glass fermenter and stainless steel fermenters. As I told you already, glass fermenters are mostly used for small scale fermentation process, and stainless steel vessels are mostly used for large scale fermentation. Glass fermenters, if you see, what you see in the image are example of a glass fermenter. The left side image is the fermenter, glass fermenter, and the right side image is a glass fermenter with the automated connections. Usually, glass fermenters are preferred. Why? Because they are they have a smooth surface. They are non-toxic to microbial process. They are corrosion proof. They are easy to examine. That is most important. You can see through. You can see what is happening inside the fermenter. Easy to examine the interior of the vessel. And sterilization, we usually do it by autoclaving, because mostly the glass fermenters are very small, 1 liters 2 liters capacity. We can keep them as such into the into the autoclave, and we can do the autoclaving. That means sterilization is done by autoclaving. These are small fermenters which can be autoclaved in an autoclave. And the diagram you can just see, they are example of glass fermenters. Stainless steel fermenters, the left side image is the cylindro-conical small fermenter, which mostly people don't use as for small scale. They don't use it, but the right side you can see large scale. Usually stainless steel is preferred for large scale. The one you can see in the diagram is the bigger fermenter, or one pilot fermenter is nearby. So in this pictures you can see small scale, pilot scale, large scale, all the sizes of stainless steel vessels. Stainless steel vessels are mostly costlier compared to glass fermenters. It is most costlier to make stainless steel vessels, but advantage is that by adding chromium into the stainless steel, you will prevent corrosion, so it will become corrosion resistant. You can do sterilization by passing steam for this fermenters. Molybdenum is added into the fermenter for making the fermenter vessel, which will protect the vessel from corrosion and acid corrosion as such. So modern fermenter, the diagram you can see, this is a modern fermenter, how it looks. Vessel as such will be one vessel, but you can see the control systems are very complicated to look. So many pipelines are connected, and the things look very complicated. Why? Because everything is automated in the industry, and this is how a modern fermenter looks. You can't just identify which pipeline goes where, but this is how a modern fermenter looks. Everything is automated, fully automated. Now coming to our topic, main parts of the fermenter. See, fermenter, typical fermenter you have seen in the last PPT. Basically, the main parts of a fermenter are three. One is temperature controller, is one component, main part of the fermenter. One more is agitation, one more is aeration. Put together, these three are said to be the main parts of fermenter. Temperature control as such, what it will do is, there will be heating coils inside the fermenter, like coils in your heater. At home you have geysers. How the coil will be there inside one inside the geyser, same way coils will be there inside the fermenter. It is called heating coils, or coils may be present outside also on the wall of the fermenter. That is called as cooling jackets. Heating coils and cooling jackets, this is the parts of temperature control. Agitation, usually we call that central tube as impeller. In case of aeration, we call it technically as sparger. So let us go for today's PPT. Let us see temperature control first. Next PPTs we will see agitation and aeration in detail. Okay, temperature control. The question asked is how heat is produced during fermentation process. Now, why temperature has to be controlled? This question can be answered with this point, that temperature control is necessary. Why? Because heat is produced by microbial metabolic activity. See, we are using microorganism which is metabolically very active. During metabolic activity, they will produce heat. Heat is released as the end product of their metabolic activity, and this heat which is generated and released will heat the fermenter. So microbial metabolic activity will generate heat. Next reason for heat generation is mechanical mixing. Mechanical mixing, because when you are constantly mixing the media, that also will generate heat. So this is the reason for heat generation during fermentation. Next, how to control temperature in large fermenters. See, we are not talking about lab fermenters, we are talking about fermenters which handle 10,000 liters, 1 lakh liters of medium. In such huge vessels, how to control temperature? Practically to tell, it is impossible to control the temperature in such huge vessels. Very, very difficult or practically impossible to control the temperature. So that is what is the general concern. But still, if though it is used till it is impossible, still something has to be done to manage the temperature. For that, we employ a few mathematical calculations, and using all these things, mathematical calculation, some we can just control the fluctuation. As you can see the last point, you can't keep the temperature. If you want 37, you can't keep 37 exactly, you can't maintain 37, you cannot accurately maintain 37, but you can handle large fluctuation. You can see that it doesn't reach the 28, you can see that it doesn't reach 42 or 43, that only you can do, but you can't maintain 37 exactly. Plus and minus 7, you can manage this side and that side. That is what we call it as temperature management. So perfect 37 if you want to manage, practically we call it as impossible. So what we do here is managing it plus or minus, that is what we can do. So how to control temperature? Uh, to control temperature, few criteria we have to remember. What are the criteria? First thing is fermenter size. Fermenter size means usually, if you want to control temperature, what is the size of your fermenter plays very important role. That's the first important point. Second thing is microorganism. Which microorganism you are using? Are you using a bacteria, a fungi? Whether you are using highly aerobic or facultative anaerobe, all these things matters. Next thing is cultivation temperature. What temperature you want? Whether you want 37, 30 degrees, 45 or 28, which temperature you want, that you should be knowing. Next thing is optimum range. Optimum temperature range means what temperature your microorganism prefers to grow. See, if it may grow at 35, the point is whether it can grow still at 30 and whether it can grow at 40. That means its optimum range should be large. 30 to 40 means at any temperature between 30 to 40 it should be able to grow. So that optimum range you should know. For every organism, optimum range will vary. Suppose you are using fungi, optimum range will be between 20 to 30. Bacteria 30 to 40. Some bacteria it will be 40 to 50. So that range you should know before you can calculate. Next thing, one example I have given here, just you can observe it. Example is how to bring the temperature of a fermenter from 120 degrees Celsius to 30. That is a question asked just to solve the problem. 120, because after autoclaving it will be 120, so it has to cool. See, you can't, if you don't cool it, no, it will take day, it will take one full day, it will take 1.5 days, it will take to cool. So how to cool the vessel from 120 to 30 degrees? Inside media is there, so how to cool it? So for that, what you have to do is you have to see what is the size of the fermenter. So the size of the fermenter is you are doing 55,000 liter fermenter, that is 55,000 liter medium capacity fermenter is there. So inside the vessel it will be 60 meter square area inside the fermenter. Keeping all this in mind, the calculation tells that if your cooling water is 14 degrees Celsius, you can circulate it continuously for 4 hours. Then you can bring down the temperature from 120 degrees to 30 degrees. So this is what we call it as calculation. That helps us to find out how much of cooling water is required, for how long you have to use the cooling water to bring the temperature down, how many hours is required, and what is the temperature of your cooling water, size of the vessel, all these things matters. This is a very important calculation. It will help you to understand the what you call it as how to estimate heating cooling requirements. So you can just see it tell it what you see here is overall energy balance of a fermenter. So we call it as overall energy balance of a fermenter. In that you can see that there is an equal sign. Can you see there in the calculation, in the calculation equation you can see 3 are there, q MET here means microbial metabolism. Heat generation rate due to microbial metabolism is called as QMET. QAG is generation rate due to mechanical agitation, and QGAS stands for heat generation rate due to aeration. See here, students, first three plus you have to do is equal to what is equal to what? It is equal to Q accumulation, that is heat accumulation rate, plus Q evaporation, that is heat loss rate because of evaporation, and Q uh, sensible, that is rate of sensible enthalpy given by the flow stream. So what it is told is the first three, that is metabolic activity of microorganism, agitation plus aeration, all these things will is whatever heat is generated during this is equal to how much of heat can get accumulated in the system, and how it is exchanged, and how it gets evaporated, and the enthalpy. Putting this is called as the overall energy balance of a fermenter. So using this, what we can find out is that if you rearrange the equation, just rearrange the equation, uh, Q, that is what we have to calculate here is heat transfer rate to the surrounding. That is what is we want to calculate heat exchange, how heat gets exchanged. So heat exchange rate, that is how much of heat transfer rate to the surrounding is equal to all these things, that is first three parameters are plus, and remaining parameters are minus, that is metabolic activity plus agitation plus aeration, you have to add it up, and you have to minus it with the three more components. If you do it, you will get a value. That value, whatever you get, we call it as Q exchange. It is the heat which has to be removed from the cooling system. So using this calculation in the industry, people calculate how much of cold water has to be supplied to bring down the temperature of the fermenter to the optimum range. So after, by this calculation, I have given you an example below. By doing this calculation, people have found out that for bacteria, a normal bacteria, 500 to 2000 liters of cooling water has to be supplied per hour to bring down the temperature to 37 degrees somewhat. And for fungi, you can see 2000 liters to 10,000 liters per hour has to be supplied to bring down the temperature. Why this difference? You can see that bacteria requires less cooling water, that is amount of water required per hour is less compared to fungi. Fungi requires 5 times more water. Why? The reason is fungi will generate more heat, and if for fungi the temperature, optimum temperature is well below 30, but for bacteria optimum temperature is 37. Because high temperature, less cooling required, that is why water consumption for cooling is different for bacteria and fungi. And finally, you can see in this diagram, temperature we usually control it by using on the wall of the fermenter, you see there is a cooling jacket, we call it as. This cooling jacket will have one inlet and one outlet. Cold water will enter through one inlet and cold water will be through outlet, it will be going out. And there is a valve to control the flow of water. You can increase or decrease the flow of water. By this we can control the entry and exit of water. And this is the PPT which will help you to understand one main part of the fermenter, that is how temperature is controlled. In the next PPT we will be studying about agitation and aeration. So this is how the flow goes. Let us stop our class with this topic.